So multiplying a number and its vortex sum result in the same vortex sum, and this is it's a mouthful, but this is pretty much the crux or the main reason or main causation of most vortex math patterns. So let's go further. So note that a quote factor of 9, which I've been stating a lot, a factor, but I didn't explicitly write it down earlier, but I'll just write it down now. So note that a factor of 9 simply means a whole number that can be divided cleanly by 9. For example, 27 is a factor of 9 because 27 divided by 9 equals to 3. 9 is a factor of 9 because 9 divided by 9 equals to 1. Also, you could do this for any other number. So 9 is a factor of 3 because 9 divided by 3 equals to 3, just a whole number. Alright, let's go further. So now recall that when we write numbers as factors of 9, then the remainder that isn't part of the factor is equal to the vortex sum in base 10, which I showed earlier. So, which I proved earlier or derived earlier. So if we have 11, V equals, to get the vortex sum, just digit sum, 1 plus 1 equals to 2 equals vortex sum. Now let's go further. So if we have 11, you could also write this as the factor of 9. 11 equals 9 plus 2, which is a factor of 9 plus remainder, and 11 mod 9 is just a remainder formula or calculation algorithm that you can use to quickly calculate the remainder, and equals to 2, which is remainder, and vortex sum equals to the remainder, which is quite fascinating in and of itself. So now if we multiply 11 by 6, we get 11 times 6, just a random number. Here, 11 times 6 equals 66. Now V equals, to get the vortex sum, just to see what happens when we multiply, equals to 12 right here. So 11, so V equals 6 plus 6 equals to 12. V equals, reduce it again because this is greater than 9. It's not a single number. So this is going to be 1 plus 2 equals to 3 right there. Or we could write this as a factor of 9. So 11 times 6 equals to our 11, which is our 9. 9 times 9 plus 2 is just right here, which is equal to a factor of 9 there. So what we're going to have is equals to 9 times 6 plus 2 times 6. Because when we multiply this inside, and but this is still going to be a factor of 9 because 9 times 6 divided by 9 is just going to be 6. Or a factor of 9 times by a factor times by any number, it's still going to be a factor of 9. Because you're still gonna have a whole number. Now we're just gonna be multiplying this whole number. For example, if you have 27 over 9 equals 3, if you multiply 27 by 3, 4, 5, 6, all you're doing is gonna be multiplying this 3 by 3, 4, 5, 6. So you're always gonna have a whole number. So in other words, it's always gonna be a factor of 9. So when we multiply this inside, 9 times 6 plus 2 times 6, we're gonna have here. This is just a factor of 9. Because number 9 times 6 divided by 9 is just 6. And then we have a remainder or partial remainder because it's going to be greater than 9, 2 times 6. So note that both 11 and 11 times 6 are both written as a factor of 9. In other words, we have 11 equals to a factor of 9 plus 2. And 11 times 6 is a factor of 9, which is our 9 times 6. Doesn't matter what it is. It's still a factor of 9. So it does not count for the remainder. So then we have 11 times 6 equals a factor of 9 plus 2 times 6. Since the remainder governs the vortex sum, then we just have to compare the remainder. For example, 11 V equals 1 plus 1 equals 2 equals the vortex sum. The remainder is 2, which is also equal to the vortex sum. And notice here, 11 times 6 equals to 66. V equals 6 plus 6, which equals to 12. V equals to 1 plus 2 equals 3 equals vortex sum. And then if we just take the remainder equals 2 times 6 equals 12. V equals 1 plus 2 equals to 3. In other words, here I just took the vortex sum of this remainder, which is 2 times 6. And that's going to be equal to the exact same thing. Note that multiplying 11 or its vortex sum 2 by 6 results in the same vortex sum. These are the exact same ones. This is absolutely fascinating stuff. So now, for example, if we have 11, let's write this down like this. V equals 2. This is the vortex sum equals to 2. Now if we multiply 11 times 6, we get 66, and then this V equals the vortex sum is going to be equal to 3. And we could have done the same thing here. So times by 6 over here, and then we're going to have a 12. V equals to 3. So these are the exact same. So these are the same thing. Yeah, and here I just quickly rewrote this. So same. So these are the exact same stuff. And we can in fact prove this is the case for any integer and in any general based number. And so if we have n equals to just any base for any base number system, and then p equals to n minus 1, or the base minus 1. Then what we have is, and also let's say we're given a, b, c, as before, is any integer between 0 to p. Then also I'm going to define capital A equals to integer, and this is just equal to these this a, b, c, and these corresponding digits right there. So if we have a equals to abc, or capital A equals to lowercase abc, then you can just break this up into its parts for any number base number system. Here we'll have a times 100 plus b times 10 plus c, and then we have a, and then break this number 100 up based on its number system. In this case, p is the largest digit, so we can have a equals, or this equals to a times pp plus 1, and then b times, this is a 10, p plus 1, and then c is just c times 1, just ignore the 1, just leave it. So it's plus c. This equals to now a times, and just multiply this inside, a times pp plus a times 1, which move those to the right, the a times 1 and the b times 1. So then we're going to have a times pp plus b times p plus a, plus in this bracket, a plus b plus c, where again, this one right here is our factor of p. And then this part right here is our remainder, or remainder until when we take when we repeat the process, remainder. When we repeat the process until we have the remainder is equal to just less than p, so that it's equal to the vortex sum, and hence the remainder, or the a mod p value right here. So that's the remainder, and again, when we get to one single digit, so that it's the vortex sum. But yeah, when the remainder is 0, then that's just a mod p is equal to 0, and then we just set that equals to p for vortex math purposes. So anyway, so this is a factor of p plus remainder. So that means our capital A is equal to a factor of p plus, I'll call this R1, which is, because we're going to deal with R2 later. So R1 is just a remainder, and you could calculate that as a mod p, and it's just a vortex sum of a, which I proved earlier. So thus, if we multiply a by an integer multiple k, or multiplied by an integer k, it's already, by k, we have k times a equals to k times a factor of p plus r1. Yes, we have this, and we multiply that inside, we're going to have k times a factor of p plus k times r. So note that k times a factor of p, really this out like that, so k times factor of p is just a factor of p still, because for example, i.e. 2 times 9 equals 18, and 18 divided by 2 is equal to 9 is the whole number. So in other words, if you have 2 times any factor of p, you could just still go, for example, 3 times 9, you just multiply, this is a factor of 9, but you could always divide by 9, and it always goes evenly, just cancel. So it does not matter. So if you multiply factor of p, it's still going to be a factor of p, and then since the remainder is what governs the vortex sum and the mod function and the remainder, that's all it is. So we don't need to look at this k value. So this k times a, this just becomes this over here. So we replace the k, just becomes a factor of p. So k times a equals a factor of p plus k times r1. So that means it's a new remainder. So k times r1, this one, assuming it's greater than p, we could also write this as a factor of p plus a new remainder r2. So we could write this one here, that's just the remainder part, we just reduce that further. So then r2 is equal to new remainder equals to just k r1 mod p, which is just a vortex sum of k times r1. So that's what we have. So this vortex sum is for this remainder part here, but again, this remainder, we could write this as a factor of p plus r2, and then we could just throw that back inside this full function, this k times a, so the k, the multiple. This one is k times the first vortex sum, which was over here, which is for this a value there. So that means if you just replace this k times r1, that's over here. That's this whole side there. So then what we have is here, factor of p, which is this part, and then plus factor of p plus r2, which is this k times r1, when we could reduce, or rewrite it like this, when we keep reducing it until we get a remainder. And so what we have is this, but we also note that factor of p plus a factor of p is still equal to a factor of p. So again, all we want to do is get the remainder. So for example, i.e. 9 plus 9 equals 18, 18 divided by 9 is 2 is a whole number. And again, when you add stuff, for example, 9 plus 9, you could always divide by 9 because they just cancel. It just becomes 1 plus 1 is 1, 1. And this equals to 2. Yeah, so thus we can write this part. Yeah, we can write this whole part right here, k times a, and this just replaces factor of p plus factor of p. It's still just going to be a factor of p. So ka equals factor of p. Anyways, hopefully you like my next level derivation skills right here, or deriving skills. So yeah, in future videos I may do a more formal proof, but again, this is pretty next level. So k times a equals factor of p plus r2, and r2 is a new remainder for this ka. And then this we could just solve it by K8 equals, Ka mod P, which equals the vortex sum of K times A. So thus, yeah, notice this is the R2 is the exact same as this one here. Like that. We already solved that for in a different method. So thus, the vortex sum of Ka is equal to the vortex sum of Kr1. And we know that R1 is just equal to the remainder equals the vortex sum of A. So it equals the vortex sum of A. And k times a equals factor of p plus r2, and kr1, yeah, because kr1 equals factor of p plus r2. That's what we solved over here. So kr1 is factor of p plus r2. And then we have ka equals factor of p plus r2. So these are the exact same stuff here. And when we're dealing with remainder, these have the same remainder, so they're going to have the same vortex sum. So thus R2 equals vortex sum of Ka equals vortex sum of Kr1. And again, K times R1 is K times vortex sum of A. So in other words, vortex sum of K times A equals vortex sum of K times vortex sum of A. Or we could write this in mod form, or Ka mod P, which gets the vortex sum of Ka, equals to K times, then there's A mod P, which is vortex sum of A, and then then the mod P is going to be the vortex sum of, or the remainder of K times the vortex sum of A. So yes, I'll go over the mod. This is just a mod identity, a multiplication identity, which I'll cover in a bit. So yes, it's fascinating stuff. So in other words, the vortex sum of K when you multiply a number here, the vortex sum of this multiple of K A is equal to a vortex sum of just K times the vortex sum of A. And there was a remainder. So, for example, and this will be very, very useful, and this is actually pretty much the causation of most vortex math patterns, as I will go over soon, or we'll discuss in a bit. So, for example, consider the number 17 in base 10 and multiplied by 4. Yeah, so we have 17, V equals vortex sum, 1 plus 7 equals 8, and this is vortex sum. So now if we have 17, this also, you could write this down as 17 equals to 10 plus 7, and then this is base 10, so then break the 10 into a 9 plus 1, move this 1 over to the other side, so we'll have a 9 plus a 1 plus 7, add these up, this is going to be 9 plus 8, where we have factor of 9 plus a remainder. The remainder is 8, that's the vortex sum, it's less than, it's a single digit. Yeah, so we have 17 mod 9 equals to 8. And yeah, you can just type that in. Let's just verify this. Equals 8. Yeah, equals remainder equals vortex sum. So we're all good right here. That's for the number 17. But now we have k equals 4. We were going to multiply 17 by 4. So if we multiply 17 by 4, we get 68. 68 like that. V equals, then do the vortex sum. 6 plus 8 equals 14. Do that again. V equals 1 plus 4 equals 5 equals vortex sum. And also you could break this up into its parts. So we know this 9 plus 8 is 17. So if 4 times 17 equals to 4 times 9 plus 8. Then break that down. We got 4 times 9 plus 4 times 8. So 4 times 9 is just going to be a factor of 9. Multiple of factor of 9 is still a factor of 9. Equals factor of 9 plus partial remainder. And that's because this is going to be greater than 9, so we have to reduce that again. But nonetheless, so we have a partial remainder right here, 4 times 8. But here, if we just take the 4 times 17 mod 9, this equals to 5. So in other words, we could find the remainder like using the mod function of this 4 times 17, or we could just look at this partial sum 4 times 8, which is just 4 times the vortex sum of 17. So in other words, 8 times 4, or 4 times 8, equals to, let's put this 4 times 8, put that in front, just so it's in line with everything, because we have the 4 times 17 right there. 4 times 8 equals to 32. V equals 3 plus 2 equals 5. Yeah, so then, and then we have 32 mod 9 equals 5. So in other words, multiplying the vortex sum here, and then doing the vortex sum gets the same as multiplying by this and taking the vortex sum. So this is true for any base, and this is this is where we understand that everything we're used to is all base 10, especially the built-in calculators. So this is true for any base. So for example, let's look at base 8 right here. 15 in base 8. The vortex sum is 1 plus 5 equals 6. So that's a vortex sum, as you add these digits. And then we have, but then if you want to write this in a remainder form, we're going to have 15 base 8 equals to 10 plus 5. But now the 10 is its relative value based on base 8, so it's going to be 7 plus 1 plus 5. And then we move this 1 over to this side. So we're going to have a 7 plus, plus 1 plus 5, like that. So in other words, we have, this is the vortex of 1 plus 5. 7 plus 6, add those up, equals to a factor of 7 plus remainder. 7 is the highest unique digit in this base 8 system, or 8 minus 1 is 7. Yeah, so that's what we have. 6 is the remainder. That's a vortex sum right here. But then now, if you want to use the mod function, this is built in base 10. So we're going to have to go convert this to base 10. 15 in base 8 is equal to, well, relative value of 10 is 8. So 8 plus 5 in base 10 equals to, well, add those up as 13. And then we're going to have 13 mod 7. This equals to, 6. So remainder equals vortex sum. So fascinating stuff. So now we're going to multiply by 4. So we can multiply this 15 by 4. So 15 times 4 in base 8 is equal to, well, we know it's 10 plus 5. 10 plus 5 times 4. And then, so when we multiply this inside, we have 10 times 4 is 40. Then we have a 5 times 4 right here. But then we can't just calculate that directly because this is, again, built in base 10. So to do that, we want everything in 8s. And 8 is equal to a 10. Remember, an 8 base 10 is 10. So we always think of the relative value and then convert it into a number 10. So we're going to break this number 5 into 2 plus 2 plus 1. Yeah, so that's just 5 right here. 2 plus 2 plus 1 equals 5. And the reason we're doing that is because we have a 2 times 4 is 8. So 40 plus 2 plus 2 plus 1 times 4. We're going to have this 40 plus and then 4 times 2. And then right here, this one's already done. It's already there. We're going to have a 4 times 2 equals to 10 in base 8. Remember, the value is 8 in base 10, but again, we want we want the base. We want them all in 8s for base 8. We're dealing with base 8, so an 8 is a 10. An 8 in base 10 is a 10 in base 8. So this is going to be 4 times 2 is 10, plus 4 times 2 is 10, plus 4. So we're going to have a 40 plus 10 plus 10 plus 4. You can just add these up normally because you don't get beyond the number 8 right here, or 7. We don't get greater than 7 in any of these digits. So we're going to get a 40 plus 10 is 50, plus 10 is 60, plus 4 is 64. So you have 64 right there. And now let's just write that down right here. So what we have is 15 times 4 in base 8 is equal to 64. And then take the vortex sum v equals 6 plus 4. And then again, we can't just add them up normally. So we have to go 6 plus, break the 4 up into 2. So 6 plus 2 plus 2. This is an 8, but isn't actually a 10. It's in base 10. It's going to be 10 plus 2. So equals 12. V equals, I don't know why it keeps popping up this right here. But anyways, we get a 12, then v equals 1 plus 2 is 3 equals the vortex sum. So that's doing that manually. And now we have 15 times 4. Yeah, 15 times 4, this is the manual way, but now if we write it in our factor of 7 plus remainder form, we have 15 times 4 equals to 7 plus 6 is our 15. That's right here. 15 is equal to 7 plus 6. And then, so 7 plus 6 times 4. And then 4 times 7, that's a factor. You just multiply these out. 4 times 7 is a factor of 7, and then plus 6 times 4. So we have a factor of 7 plus a partial remainder, because again, we've got to reduce these further. So what we have, that's a 6 times 4. So in other words, 15 times 4, we'll deal with the partial remainder inside here. That's just, that's the next part. So, but now if we want to write this in base 10, so 15 times 4 base 8 equals 2, well, you can just add these up. This is 7 plus, that's 7 plus 6. You can just add those up, or you could also look at this. We already calculated this one. This is already 13, like that. So this is going to be 7 plus 6 is 13. Just add them up normally in base, because everything is base 10 by default, especially in my brain. So 13 times 4 base 10 equals 52. There you can just see that it's true, equals 52. Alright, so that's 52. And then 52 mod 7, this equals to 3. Like that. equals vortex sum. So now if we look at this partial remainder though, this partial remainder just states this is a vortex sum of 15 times it by 4. So we could just calculate that instead of doing the 15 times 4 at vortex sum. So 6 times 4 base 8 is equal to, and again we can't just multiply normally, so 6 is equal to 3 times 2 is 6. So then we're going to look at this part right here. 2 times 4 is 8, so we'll just replace that with a 10 in base 8. So 3 times 10 is 30. And now we can calculate the vortex sum of it. So 6 times 4 base 8 equals 30, v equals 3. It's 3 plus 0. Yeah, so that's doing the manually, just multiplying and then taking the vortex sum. But we could also do, we could also use the mod function by converting to base 10. So 6 times 4 base 8 is just equal to 6 times 4 base 10 because both these digits are included in base 10. So this just equals to, this equals to 24. Equals 24, like that. Let's erase that. But you could also write this as 3 times 8 because this is 30. So in other words, instead of going 3 times 10 is 30, we could go 3 times 8 is 24. So they're all the same thing. And then you go 24 mod 7 is 30. So yes, all of these are equal, every single one. And so it's true for any base, but any base besides 10 is very, very out of the box. Yeah, out of the box thinking. You gotta just make sure that each step you're doing correctly and not just assuming based on the usual base 10 adding and subtraction and number system, etc. So thus it is much easier to determine the vortex sum of the remainder, especially when the multiplied number gets very large, such as in the following base 10 example. Yeah, because again, what this says is we could just take the vortex sum initially and then multiply it, as opposed to multiplying it and then doing the vortex sum. Because the vortex sum can only be a number between 1 to the base. So it's very, very small. Base minus 1. So it can only go 1 to p, or the modulus. So thus it is much easier to just determine the vortex sum of the remainder, especially when the multiplied number gets very large, such as in this example. Let's go right here. I'm going to go, let's say we have number 64, like this. And let's multiply 64 by 4. We'll do this manually just to show in case you don't have a calculator or whatnot, or you just want to do it in your head. So it's, again, be tedious. So if you multiply 64 times 4, this equals to, 4 times 4 is 16. Add the 1 there. 4 times 4 is, 4 times 6 is 24. Add the 1, so give it 256. Like that. And now if we take the vortex sum here, v equals, 2 plus 5. Plus 6, this equals to, this is going to be 7 plus 6. 7 plus 6 is going to be, 10 plus 3 equals to 13. Like that. Equals 13, but instead we could have just done this one right here, the 64. If we just did instead go v equals, for the 64 is 6 plus 4 equals to 10, v equals to 1, 1 plus 0. And now we multiply this by 4. Times 4, this equals to, 1 times 4 equals to 4. Oh, this one we forgot to add this one up. V equals 1 plus 3. Yeah, so we're still not done that one, and we finally got it. 4. But this one already there, 4. So this one you can just do it in your head. 6 plus 4 is 10 is 1, times 4 is 4. This one you have to multiply this manually. 64 times 4 is 256. Add up every single one. Add up again. And then add up again. And these are the exact same thing. So yeah, so now you understand how powerful this one is. This is super, super simple and easy. Yeah, and more importantly, if the vortex sum is the same as a previous multiple, then a pattern arises. And that's because, if you're doing a series or sequence of patterns or vortex sums, and you're using the same multiple, and then if the same vortex sum arises as a previous multiple, that means we already know what it's going to be when you multiply it, because we've already done it before. So because we don't need to care about what this number 64 is multiplied by 4. We don't care if it's 256, whatever. All we care about is this number 4. So if we have this number 4 showing up again, or another number, or a similar number showing up, then a pattern arises, and I'll illustrate that soon. And this is basically the causation of most vortex math patterns. And this can be seen visually by considering the following vortex sums. So let's say you have number a, and then the vortex sum is equal to 1. And let's say a times k, the vortex sum is equal to 2. And then a times k, so you just multiply it by another k. V equals to 4, and let's say you multiply it again by k, and then the v equals to 8. Then you multiply again, it equals to 7, and then multiply again equals to 5, and multiply again equals to 1. And now we don't care anymore about what this actual vortex sum is. We know it's going to, the next multiple is going to be 2, because we already know that the vortex sum of A times K V equals 2. Remember, multiplying this by K gets this, but you could have also multiplied this, right, or 1 times K. Yeah, V equals to 2. Yeah, so these are the exact same stuff here. So we could have got to this 2 from just multiplying this, the vortex sum of A. So in other words, we already know what this one is, and we already know what this one is. This one's going to be based on this number 2, so we don't care what these big numbers are. So even though this number gets super, super large, it does not matter. It's going to be dependent on the remainder, or the vortex sum. So in other words, the next one's going to be 4, the next one's going to be 8, the next one's 7, the next one's 5, the next one's 1, the next one's 2, etc. Pattern repeats indefinitely regardless of how big this number is. So note that I used the typical 1, 2, 4, 8, 7, 5. So yes, 1, 2, 4, 8, 7, 5. 1, 2, 4, 8, 7, 5. Doubling pattern, in other words, K is equal to 2. So yes, 1 times K, 1 times 2 is 2. I.e. K equals 2, pattern referenced by Marco Rodin is the main one right here, and I'll go over it later in this video as well. So thus, even though there are infinite amount of numbers and they get super, super large, there are only a finite number of single base digits, or single digit base numbers. In other words, we can only have from 1 to 9 for the vortex sum, or 0 to 8 for the remainder, or the mod function. So thus a pattern is almost always expected. Yes, you're always expecting a pattern. So that's absolutely fascinating. This is the causation of it. So yes, absolutely magical. Almost always expected. This is right. Let's bold that. That's pretty amazing.